Yeah, camps on everyone. Let's start off. There, last class we have finished with wave optics. We'll be starting with modern physics today. Hope everyone has started, solving wave optics. Do finish your material. Don't delay it because these chapters, right, you won't get again time to revise. Take a time till next Wednesday and try to wrap up your waves and wave optics ka thing. That is one. So next thing, modern physics. So in modern physics, right, we have five subparts, which is photons and photoelectric effect. And then we have Bohr's theory. These are the two major things. And then we have X-rays and nuclear physics and radioactivity. Now, radioactivity is removed from the mains portion, but it is there for advance and bits. So we are going to do it anyways. Okay, so today we'll be starting off with the photons and the photoelectric effect. Again, not a tough chapter. You will see a lot of terminologies, right? Will be similar to your chemistry, but the kind of problems we will do will be more of mechanics oriented, right? So let's see. So what are photons? Photons are packets of energy which are massless and travel with the speed of light. So basically, they exhibit the particle nature. Means they will do everything a particle does. Like, there'll be collisions, right? There'll be momentums. When they hit a wall, they're going to exert force and all that stuff. Properties of a photon. The first thing, this you studied in chemistry, the energy of a photon is given by E is equal to hc by lambda or h into frequency. I am using f for frequency here. H is a Planck's constant. 6.6 into 10 power minus 34 joule second. C is the speed of light. Lambda is wavelength. So if you substitute all these values here, you'll get energy in joules. But when you talk about these photons and everything, right, these energies are so small, we prefer to study them in electron volts. So we have a formula for this. So this is 12400 Y, that will be in EV. Here lambda must be in angstroms. Example, let's say if you have lambda 6200 angstroms, then the energy of the photon is 2 eV. What is 1 eV? So this 1 eV, actually you should write this thing as E into 1 volt. So E is the charge of an electron and 1 volt is like Q into the potential difference. So 1 eV is the energy gained by an electron when it moves across a potential difference of 1 volt. When you say 10 eV, means if you take an electron across a difference of 10 volts, that is the charge energy gained. So EV is simply the energy gained by an electron. So E is the charge and V is that voltage. Energy gained by an electron. When it is taken across a potential difference of 1 volt. Clear with this? This is the standard stuff which you know from your chemistry. Clear with this? Next thing. If you see the energy emitted in the radiation is integral multiples of h into f. Means you can't get half photon or 1/4 of a photon energy. So it should be always multiples of hf. We call this thing as quantization. We studied this in electrostatics also. Charge is quantized, so all charge transfers are integral multiples of electronic charge. Photons are unaffected by electric and magnetic field. They don't have any charge. Photons are massless, but they have momentum. So you cannot use the formulas which you use for actually, particles with mass. The momentum of a photon is given by h by lambda. There I'm putting all the formulas in the red boxes. Fifth one is theoretically important point. A photon, right, either is completely absorbed or it is completely unaffected. Meaning, we'll talk about that. I'll give an example, but what it says is, if you give a photon, right, either you take the whole photon or don't take anything. You can't say like, I'll take a part of the energy, I will take half energy and leave the remaining. That doesn't work with a photon. Or unaffected. And it can be absorbed only by one particle. Two particles cannot share one photon. So one photon can be taken only by one particle. So let me give an example. Now, let's take an example from Bohr's theory, where you have a little idea about it. So if you take this hydrogen, this is n is equal to 1, n is equal to 2, n is equal to 3. We know 1 to 2 transition will take 10.2 eV, and 1 to 3 transition will take 12.1 eV. Right? Some values you need to remember. And let's say we have an electron in the n is equal to 1, and a photon comes from outside and falls on this electron. Now, if this energy of the photon is less than 10.2 eV, what do you think will happen? The electron will say, boss, I need at least 10.2 eV for the transition from 1 to 2, and you're giving me less than that, so I'm not going to take it. Getting it? So nothing happens. The photon just passes through. Okay. What if you give 10.5 eV? Now what will happen? The electron will say, this is fine. I need 10.2. You have 10.5. So electron will say, okay, give me 10.2. But the photon will say that doesn't work with me. Either you take the whole 10.5 or don't take anything. You're getting it? So you will not get a scenario where 10.2 EV, this is one of the options. If they ask in the exam, this will be one of the options. When a 10.5 EV photon is, incident on a hydrogen, what will happen? So the electron will excite to n is equal to 2 and a 0.3 EV photon comes out. That is not going to happen. Again, nothing happens. The photon just passes through. So it's like, limitation from both the sides. A photon will say you take either everything or you don't take anything. And electron says I need only 10.2. So it doesn't work out. This is the reason whenever you shine white light onto a hydrogen sample, you will observe only certain wavelengths are missing. We call this thing absorption spectrum. You guys remember this? Studied in chemistry, absorption spectrum, characteristic spectrum. So you will see certain frequencies are missing. Every wavelength does not get absorbed. So only if the energy of the photon is exactly the difference, like 10.2 eV, 12.1 eV, and so on, right? It may be absorbed. Again, may be absorbed. There is no 100% compulsion you have to be absorbed. You're getting that. So you will not absorb any other energy. But there is one exception though. If your energy of the photon exceeds your binding energy, in this case, if energy of the photon exceeds 13.6 eV, then the electron will go to infinity. So it will absorb, it will take everything, and that excess energy becomes kinetic energy. Because you have given enough energy to escape the complete hydrogen atom. So example, if you give energy of the photon as 15 eV, so this is one case, where the electron will take any amount if you exceed your binding energy there. So if I give 15 eV, the kinetic energy of electron at infinity will leave the balance, which is 1.4 eV. Clear with this? So there, this I combined Bohr's theory ka thing with a photon. So both of them have their own conditions. Electron in a Bohr's theory will say, boss, I need exact amount of energy. And photon will say, I can give you more, right? But you have to take everything. Clear with this? So be careful. They do frame questions of this sort. So if you send 11 eV photon, nothing happens. So, but most people will think this way. People will think out of 11 eV, 10.2 is used for transition and 0.8 comes out. And this 10.2 eV, right? It will again, electron will jump from 2 to 1. Again, you get a 10.2 eV. That is never going to happen. You can't split up. Clear with this? Next thing, de Broglie wavelength. This we saw even in wave optics. People have noticed, even particles start exhibiting, this wave phenomena like interference and all this stuff. So when you actually try to calculate, so if you see de Broglie wavelength, right, it is not real. It is an hypothetical thing. It is something which we have created. It's like an equivalent wavelength. So when you say the de Broglie wavelength of a particle is so and so, it means these particles are behaving exactly like a wave of this wavelength. They behave like. So lambda de Broglie is given by h by mv. Momentum can be written as h by root over 2 times mass into kinetic energy. M is the mass of the particle and v is the speed. Now be careful here. Don't mix up the formulas for photons and particles. In case of photons, the energy is given by hc by lambda. In case of particles, the kinetic energy is half mv square. Don't use the formulas of particles for photons and photons. This thing. Momentum is given by h by lambda. Momentum is given by m into v. Here wavelength is lambda. here, this is your equivalent wavelength, or you can say pseudo wavelength, just like a pseudo force, which is h by mv. So if someone asks you what is energy of the particle, don't write this nonsense, hc by lambda de Broglie. You're getting it? Energy of a photon is hc by lambda. So I have seen people doing this. They say, sir, but the wavelength of a particle is lambda, so energy must be hc by lambda de Broglie. Are you getting it? This is a blunder. There's nothing like that. Don't mix up stuff. Does the particle go with the speed of light? So how are you using hc by lambda? Clear with this? That's a bit of a thing about the photons. Let's see some questions. Any doubts so far? Going ahead. Let's see a question. Particles, de Broglie wavelength is equal to wavelength of a photon of energy E. M is the mass of the particle. Find the energy of the particle. So there is a photon of energy E. That wavelength is equal to the de Broglie wavelength of a particle. Then what is the energy of the particle? Try. You got a minute or two. And others, do keep your cams on. Right, Adit? See, the energy of a photon is given by hc by lambda. So lambda photon is hc by E. And in the question, it is mentioned lambda photon is nothing but lambda de Broglie. So this Sc by E is equal to h by root over 2 times mass into kinetic energy. This will be c square by E square is equal to 1 by 2mk. K is equal to E square by 2mc square. Easy? Yeah, a simple main level question. It's an easy one, but you need to know your formulas and you need to understand what is being asked. Let's see one more. We got a disk here of radius r, and at a distance of r by root 3, there is a light bulb. Whose power is 10 watts. This thing, right, emits monochromatic wavelength, where lambda is 6,600 angstroms. find the number of photons hitting the disk. Now this bulb is going to emit photons in all directions, so some of them will hit the disk. So how many photons will hit the disk per second? Find the number of photons per second hitting the disk. Assume 5% efficiency of the bulb. That means only 5% of the power becomes light. So they will simply say efficiency of the bulb is so and so. That is the meaning of it. Let's give it a try. I'll give you 3-4 minutes. Let's see how will you approach this. Let's see. First of all, start with this. Can you find how many photons are coming out of the bulb? Let's start from there. Forget about the disk. Let's figure out how many electron photons are coming out of the bulb. So let's start from here. So what is power exactly? Power is nothing but energy per second, which is nothing but number of photons per second into energy of each photon. That makes sense? If you take energy of one photon and if you multiply number of photons per second, you get total energy per second. So here the power is only 5% efficiency. So that will be 5 by 100 into 10 is equal to number of photons per second. I'll just call it NP into energy of the photon will be H, which is 6.6 into 10 power minus 34 into 3 into 10 power 8 by lambda, which is 6,600 angstroms. Solve this, you will get the number of photons per second. I have good numbers only. This will be 1 by 2. I think you'll get something like 1 by 6 into. This is 10 power minus 3, 15, 10 power 19. Okay. Then now we have to go back to this thing. This we have done in electrostatics. If you take this disk and look at this, every photon that passes through the disk also passes through this curved surface, isn't it? So can I say like this, the number of photons passing through the disk must be equal to the number of photons passing through the curved area. number of photons through the disk, and that curved area must be same. This is what we have done in electrostatics Gauss law for calculation of flux. You should refer that in case you forgot. Yeah. Remember this question? There is a point charge q in front of a disk and find the flux passing through the disk. We use that same argument here. Every line that is passing through the disk will pass through that sphere. And this formula for area, right, we saw first time in calculus. Page 110, calculus, you should refer that in case you forgot this. So I can argue a statement like this. So for a full area of 4 pi r square, the total number of photons are NP. Now for this area, so this curved area will be 2 pi r square 1 minus cos theta. That will be the number of photons in the disk. Therefore, we get the number of photons in the disk per second will be number of photons per second by 2 into 1 minus cos theta. In case you don't remember. This came, I think first time you saw this in calculus, then you saw this in friction, then you saw this thing in electrostatics. And now again, this is so this curved area is given by 2 pi r square 1 minus cos theta. In our question, theta is 60 degrees. You can substitute and finish it off. Tan 30, tan theta is root 3. So the number of photons through the disk will be 1/4 of number of photons. Clear with this? Check it out. So that would be the important thing. So every photon that passes through the disk will pass through that curved area. So for full 4 pi r square, a sphere, it will be the total number of photons. For this much area, how many photons will be there? This question is quite similar to your Fluxka question. Next thing. Clear with this? Daria, clear with this? Nikhil? Anshul? Clear. Arya? Aditya? Next one. We got a cube here of side 1 centimeter. Again, if you see, I'm not teaching you anything out of the world concepts. All the things which you learned in chemistry, that hc by lambda and all that stuff, you're just using that in a little different way. So we are just taking, from different parts of physics, we are taking things and we are dumping it. So here we have an intensity I. What is intensity? Power per unit area. Seeing this in waves, which is 10 watt per meter square. Lambda is 6,600 angstroms. Now, if these photons are falling into the cube, right? Now, these photons are passing through the cube. So every second, the number of photons entering is equal to the number of photons leaving. That means at any point of time, there will be some photons inside the cube. Find the number of photons inside the cube. I'm not asking you how many photons are passing through the cube. How many photons are inside the cube? Let me give you an example. See, for example, if I have a room here and we have a people, let's say people are going every second, 5 people are entering the room per second. 5 people are entering the room per second. Okay? So when these people are entering inside, so when this person leaves here, one person will enter here. So one person leaves, one person will enter here. So the number of people entering is equal to number of people leaving. But at any point of time, you will see there will be some people inside the room, isn't it? So the question is, how many people are there in the room? Did you get what was the question? Try. I'll give 2 minutes and then I'll show you. Again, these all are proper mains level questions. The previous one is still a little decent one. Let's see. I don't know the number actually. Let me give an idea here. See, think of like the same example which I gave you. Let's say every second, 5 people are entering the room. And let's say the speed of each person is 1 meter per second. And let's say that length of the room is 10 meters. Can you tell me how long will it take for these people to cross the room? 10 meters ka room, 1 meter per second. So it should take 10 seconds to cross the room. So that means for 10 seconds, people are entering the room before leaving the room, isn't it? That means on the 11th second, one person will come out of the room and one person will start entering the room. That means inside this room, we have 10-second worth of people. Does it make sense? For 10 seconds, whoever entered inside didn't come out of the room. Matlab, there are 10 seconds ka worth people are inside the room. Is that making sense? If every second 5 people entered and for 10 seconds no one came out from the other side, that means all these people are stuck inside. 11th second, one guy came out, but one guy entered again. So the number is balanced. So these many people will be always inside the room. So using that logic, so let's find this. So what is intensity? Intensity is power by area. What is power? Energy per second, which is number of photons per second into energy of the photon by area. So the number of photons per second will be I into area by energy of a photon hc by lambda. This is the number of photons per second entering the upper face of the cube. Now, if you look at this, let the length of the cube be L, which is 1 centimeter. These photons are coming with what speed? Speed c. So how long will it take for the photon to pass through the cube? L by c. This is the time taken for a photon to cross the cube. Now think about it. Every second, this many photons are entering, and it will take this much time for them to come out. That means all the photons that entered inside for this much time would be staying inside. So number of photons inside the cube will be number of photons per second into time. This will be IA lambda by hc into L by c. You know all the numbers, you can substitute and get it. I'll leave it to you there. Clear with the steps here. Decent question. Yeah, next one. Keshav, clear? Sharman, Vojas, Tanvi, clear with this? Next one. The next one, you have seen this in fluid mechanics. We have a surface which is perfectly absorbing, sending a light beam. Now see, if light momentum, if photons have momentum, that means when they collide, they're going to exert some force. I is the intensity of the light beam. So this light beam hits the wall and gets absorbed completely. And A is the area of cross section. Find the force and the pressure acting on the wall. This is perfectly reflecting. It's sitting at an angle and bouncing off. Find the pressure and the force acting on the wall. If you see this line, fluids, that's exact same question. Say, wall is hitting, and wall is water jet is hitting at an angle. So instead of water jet, we made it a light beam. Try. First was easy. Think about that. I'll give you a minute. Second is the most important one. And then I'll show you how they can combine both also. But take a minute or two. Get the first one. Think how you approach this. No, just that is wrong. Okay. Get the second one also then. Right, Advait. First was easy. Right there, yeah. So think of like this. Let the number of photons be n. Now we don't know how many photons are hitting the wall. Let the number of photons per second hitting the wall be n. Force is nothing but change in momentum by time. So what is the change in momentum here? This is the number of photons per second n into h by lambda. So this is the momentum of one photon. Remember, it is getting absorbed. And this will be the number of photons per second. So when you multiply them, you get the total momentum per second. And Newton's second law, total momentum per second is nothing but force. Isn't it? That's your Newton's second law, F is dP by dt. So F is equal to N multiply with C and divide by C. Now suddenly hc by lambda becomes energy of a photon. So N is the number of photons per second into energy of a photon becomes total energy per second. Energy per second is nothing but power. So force is nothing but power. Power is nothing but intensity into area. And force by area becomes pressure. So whenever it's perfectly getting absorbed, the force is IA by C and the pressure is I by C. And the best thing about this formula, since this pressure is coming due to radiation, we call this thing radiation pressure. This is the fifth type of pressure that you're handling with. The first one was fluid pressure. Then you handled electrostatic pressure, gravitational pressure, magnetic pressure, radiation pressure. And the thing is, as long as it is pressure, everything that you have learned before will be valid. So if you give me some random amoeba surface here, and if you shine a parallel beam of intensity I, and if it's perfectly absorbing, we can use projected area. Hope you remember what is projected area. So you can just replace this entire curve with this disk here. This is your projected area. Because Emacs doesn't care the pressure is coming from where. So the force on the curved surface will be pressure I by A into projected area. Be careful, valid only when it is perfectly absorbing. So it doesn't matter what is the surface, you just need to take the projected area and finish it off. In case you don't remember what is projected area, you should go back to fluid mechanics. Projected areas come multiple times. Clear with this. What about the second case when it is getting reflected? Right, Keshav. Nathan, me, that's not the answer. Right, Vojas. What about if you're hitting at an angle theta? I hope you remember what is the catch. There's a small issue there. When you're hitting at an angle, you're not hitting at the same area. Again, if you go back to fluid mechanics, you will see this. We had a full discussion on this. Look at this discussion. Whenever the water jet hits at an angle, the water jet actually spreads out. The circle becomes an ellipse. Because in one direction it is spreading, in one direction it remains same. So the area becomes A by cos theta. So when you say pressure, it is not F by A, it is force by area where it hits. 8 cos square theta, if you remember. So I will write that page 19. Should so this area is A, this is theta, this is theta. So even though that area is A, it is spreading over this area, A by cos theta. Should refer this page 19, fluid mechanics. This whole chapter will be like this only. You will be literally bringing everything from every other chapter. So let the n be the number of photons per second. So the force will be 2 times h by lambda cos theta. This is the change in momentum of one photon because you're hitting at an angle. It's like an oblique collision into n, that is the number of photons per second. So this is delta p of one photon. And when you multiply with n, it becomes a total change in momentum per second. Then this will be 2n, multiply and divide by c. Then hc by lambda becomes energy of one photon, which is nothing but power. Power is nothing but I into area. 2IA by C cos theta. This is the force. So when you write pressure, this is where you have to be careful. Pressure is force by area where the water jet hits. The water jet is not hitting in area I, it is hitting in A by cos theta. 2I by C cos square theta. Important result. When you hit, so this is the second time you've seen this kind of thing. The previous one, it was a water jet. Now it's a light beam. Any doubts on this? Next one. Let's see a similar one. Let's say we got a surface here. We got a light beam which is hitting at an angle theta. Intensity I, area A. This thing, 60% is perfectly absorbing. So whatever light is falling, 60% gets absorbed. So nothing is perfectly reflecting, nothing is perfectly absorbing, right? And 40% is reflected. Now find the force on the wall. And remember, all these questions we are doing is simply based on photons. I didn't teach you any other concept so far. Radiation pressure, one of the important concept. Get this. Neither. It's a small catch there though. Let's see. So we have to split this into two parts. Whenever you have something of this sort, what is there to be confused? The formula is clearly written there. I know my handwriting is not great, but it's cos power 1 theta. So what is the doubt? Tanvi, clear with that? Clear, na? So let's take this thing. So to split the problem into two parts. Perfectly absorbing and perfectly reflecting. Because I know how to do for each one separately. So here I will assume there is a light beam of intensity 0.6i, isn't it? Because only 60% is getting absorbed, we'll take 0.6. And now here you have to be careful. Now when this light beam is getting hit and absorbed, understand one thing. The entire light beam is getting absorbed. So the force will be exerted in this direction, isn't it? Think about it. The photons are hitting at an angle. Not only you have a horizontal momentum, there's also vertical momentum. And now you are saying the entire beam is getting absorbed, means there is a tangential force on the surface. Are you clear with that? Think about it. Suppose if you have a ball, right? If it just goes here and if let's say E is equal to 0, you know what will happen? After hitting, the ball will just go off like this, isn't it? The ball won't stop. There should have been a tangential force in order to stop the photons from going along the wall. So the force is actually in this direction. So this F1 will be I by C into area. That is a force due to absorption. We get cos theta I cap minus sin theta j cap. You get a force at an angle. So whenever it is getting absorbed, the force will be in the direction of the beam. But when you're getting reflected, this I is 0.6 I. So this can be treated as 0.4 I. Now see, in this case, when they're bouncing off, there is no change in momentum in the vertical direction. There's only change in momentum in the horizontal direction. So here the force will be F2 only, which will be 2 times IA by C. I is 0.4. A by C, I cap. So there you can use this formula. Force is 2IA by C cos theta. 2IA by C cos theta I cap. Clear with this? But if I ask you to find the pressure, remember what is pressure? Force perpendicular to the area, isn't it? Then you won't take this J cap. If you take force parallel to the area, that won't be pressure. It's called shearing stress, if you guys remember. So pressure is a different thing. But force, when I ask you, have to take everything. Clear with this? So be careful. Even though the beam is coming at an angle, if it gets absorbed, the force will be at an angle. It's a good one. Clear with this? Nabia? Taksha? Clear with this? Next one. So we got a sphere which is perfectly absorbing. And perfectly reflecting. The radius is R. The radius is R. And now you're sending a parallel beam of light. I is the intensity. Find the force acting on the sphere. In the second case, it's perfectly reflecting. That means the light rays will hit the ball and bounce off. Find force on the sphere. Let's get this. Again, same thing. You could have played this with a water jet also. Try. It's a good one. First one is still fine. I'll give it 2-3 minutes. Think. Right, Keshav. First was easy. Remember, I told you if it's perfectly absorbing, I don't care. You just take the projected area and you finish it off. Nahi, Keshav. Second is wrong. You can't use projected area when it is reflecting. God, remember the formulas, but understand when it works and when it doesn't work. So now blindly ratta mat maro like medical students. Medical students के लिए it will work, not for us. Yeah, Navya. Right, Adit. First was kind of easy. I'm more interested on the second one. You can take 3 minutes for that. That is worth it. So since the light beam is hitting, now understand one thing. Every photon that will pass through the curved area will also pass through this disk. That means every photon will simply get absorbed. If every photon is getting absorbed, then the force is simply the pressure, which is I by C, into projected area. Like I said, it doesn't matter what is the shape. It works. How will you do the second one though? It's perfectly reflecting. How will you do? Because the problem with perfectly reflecting, the light beam will bounce off like this, isn't it? And theta is changing. Every instant theta is changing. It's not constant. Try. That's a good one. If I had to ask in advance, I'll ask you something of that sort. Right, Advait. Okay, sure. I hope you derived it. Yeah. Let's see. And I told you, whenever you see a sphere, you should know how to take an element. The first time you encountered something like this was in center of mass, how to choose elements. So if you take a small ring here, this is angle theta. This is the small d theta. So when this light beam hits and bounces off, this would be your normal. This is theta. That is also theta. So the force will be along the normal. Let me use some other color. The force will be along the normal. So this is one of the problem. Whenever you're hitting at an angle, the force will not be horizontal. It will be at an along the normal. Remember, in an oblique collision, how was the force? Along the normal. So if you take this strip, again, I'm exaggerating this. This length here is r d theta. This radius here is r sine theta. So if I open this ring, I will get the surface area dA will be the circumference 2 pi r sine theta into the width r d theta. The first time again you encountered this was in basic calculus. There, see how to find the area of a strip. You take a thin ring like this r d alpha, and when you open it, you get 2 pi r sine alpha r d alpha. This was the beginning when we did calculus, and that is how we found the whole stuff. Should definitely check that out in case you don't remember this. We got the area here. Now, what is the force on this strip? Now, be careful. There are two things here. That force is not along the horizontal. The force is at an angle theta. That means only the horizontal components add up. The vertical components cancel out. So the force on the strip will be the pressure, which is 2I by c cos square theta at an angle into area. This is the force into cos theta. You take only the horizontal component. So the total force on the sphere will be integral 2I by c cos square theta. dA will be 2 pi r square sine theta d theta cos theta. And theta limits will go from 0 to 90. Because when you go to 90, you reach the top part. You don't take the right side. Here we can use integration with substitution. You can put cos theta is equal to t. So then we end up with f is equal to integral 4I pi r square that would be minus t cube dt. Limits will go from 1 to 0. Interestingly, the answer comes out to be I into pi r square by c. You get the same answer as before one. Two reasons. One, if you think about two things that are happening. One, because you're hitting at an angle, you get more force, but the force is at an angle, so you have to take the horizontal component, the force decreases. Are you getting this? Reflection will increase the force, but the components will decrease the force. End of the day, you came up to be the same. And remember, you're lucky it happened only for a sphere. It doesn't happen every time. So don't remember this like a standard result or something. It is not true for every other shape. So just to be clear, you can try this as a homework and you can see what will be the answer. Suppose instead of this thing, if I take a cone, radius r, height h, theta here. Let's say this is perfectly reflecting. And let's say if you send parallel beam. You can try to find the force. I'll leave the answer, you can check and verify. The force will be 2I by C pi r square sine square theta. And that will be the force on the cone. So there it does depend on theta and stuff. So for a sphere, you can remember the result, but be careful. Clear this. Check out that integration. Next thing. That's a bit about your radiation pressure and stuff. The next thing, electron emission. The first thing is thermodynamic emission. This is just a bit of a theory. Just know this stuff. So whenever you take a metal and you heat the surface, it starts emitting electrons. And this is actually how you generate electrons. Later on, we will see in X-ray machine, we generate electrons and we then use them to bombard with a metal. So this is the process we generate electrons. You can think of why, because when you're giving heat to a body, the temperature T, the electrons have a kinetic energy 3 by 2 kT. And if this kinetic energy is sufficient, they can escape from the lattice. The relation for them is given by J is equal to, again, not an important formula, E is equal to minus phi by kT. So just know that the J depends on, J is your current density, current per unit area. So more electrons, more current. So it depends on temperature. So if you increase temperature, you get more electrons. A is a constant. Phi is your work function, which we will see in photoelectric effect. K is your Boltzmann constant. That means if you take a cesium and if you take sodium, it is more easy to emit electrons from cesium compared to sodium, obviously, because the binding energy of the electrons in cesium is less. This is called thermionic emission because it's due to the temperature. So the formula is not important. It is just to give an idea. It depends on temperature. Next thing. Secondary emission. If you take a surface and if you bombard them with neutrons or particles, so when they hit the metal surface, we observe electrons start coming out. Again, when you go and bombard, right, you excite the atoms inside and the electrons do get de-excited. Next thing is field emission. These are different ways you can get electrons. So if you apply really high electric field, so free electrons, meaning these electrons have come out of the atom, but they're roaming inside the lattice. And if you apply a really high electric field, the electrons on the surface will get pulled out due to the electric force. If you remember, there is something called dielectric breakdown, something similar. The electrons on the surface are pulled out by high electric field. Now, but the most important thing for us, photoelectric effect. So what is photoelectric effect? So when you shine light above a certain frequency, is incident on a surface. We observe electrons are emitted instantaneously. There's no time delay. Independent of intensity. We'll talk about that. So it doesn't matter how bright the light is. It only depends on the frequency. These are called photoelectrons. Photo, basically light-based electrons. And the effect is called photoelectric effect. This is how the picture would look. So the radiation falls on this and the electrons are emitted from there. Now, before the electrons come out, right, something like this also can happen. There is no guarantee the moment the light falls on this. This is the incident light. There is no guarantee electron will come out immediately. This electron, instead of coming out, can actually start bouncing inside and then can come out. So electron can undergo internally some collisions before it comes out. So every electron need not come out with the same energy. It's like, let's say I gave you 10 eV, you collide inside, you lose 2 eV, you collide again, you lose 1 eV, you collide again, you lose 1 eV. Now you have 6 eV, now you come out. So that is the reason whenever you're shining light, all electrons do not come out with same energy. So electrons may collide internally before coming out of the lattice. Now, when you do this experiment, what are the observations? The first thing, the electrons come out instantaneously without time delay. The moment you shine the light, electrons are out. Second thing, as long as the frequency is greater than the threshold frequency, electron comes out independent of intensity. And one photon gives you only one electron. This we discussed before. Only one electron can absorb only one photon. One photon cannot be shared. And photoelectric effect is independent of temperature. You can have a thermonic emission, but shouldn't mix up both of them. These are the observations we have when you do the experiment. This is what we see in the experiment, getting it? But the problem is, before this photoelectric effect, which is in 1907, right? If 1800s, if you see the YDAC proved in YDAC, right? We proved light is a wave. Maxwell proved that light was a wave. If you go with that statement, light is a wave, and we should have observed something else. Now let's try to understand a little about how does the energy transfer in a particle and a wave. In a wave, do you remember if you take wave on a string, how is the energy being transmitted? When you take a string and you keep generating waves, the energy is continuously flowing, isn't it? When you're sending the wave, you're sending the energy continuously. So let me give a crude example. Let's say I have a 20 kg ka water packet. Okay, and you're standing there. So what I did, I made a hole in the water packet and started pouring water on you. And I pour all the water on you. Right? So you got all the water. Do you get hurt? Nothing happens, right? But imagine 20 kg water packet, I take it and throw it on you. Now what will happen? Now you'll get smashed. Now, even though it's a water packet, right, instead made of water, the 20 kgs, when it hits you, it feels like a huge collision, isn't it? You can try this in a pool also. In a pool, now, when you go next time, take your hand and try to hit the water surface. It actually hurts. Getting it? The water surface, due to surface tension, it kind of acts like, a solid concrete. So movies may they show na hero jumps from a helicopter into the water. The first thing he will get fractures if he gets into the water like that. That is the reason when they jump, they keep their legs pretty close and they pierce the water, like, arrow going through a water surface. So the catch is this: in case of a wave, the energy flows continuously. Getting it? Whereas like in a particle, it's a packet of energy. You get the energy in one go. I hope you're getting the difference. It's like 20 kg water in both the cases, but in one case I'm giving you gently, and one case I'm just hitting you in one go. So if it is a wave, what we are assuming. So the electron which is sitting here, let's say to get out, it requires 5 eV energy. Now, if light was a wave, means you're getting the energy continuously. Let's say if you're giving 0.1 eV per second. So this is what should have happened. The electron will acquire this energy, 0.1, 0.2, 0.3, 0.4, so on. It will slowly take all that energy. It will take 50 seconds. And then it will suddenly fly out. Is that making sense? That is what should have happened if light was a wave. Instead of 0.1 second, let's say if you had given more energy, that is 1 eV per second, then in 5 seconds, you will get 5 eV, then you would have gone out. Are you getting what is happening? Means it doesn't matter what is your frequency. It depends on your intensity. If you give more energy per second, the electrons will come out faster. If you give less energy per second, electrons will still come out, but it will take more time. Are you getting it? If light was a wave, this is what you should have seen, because energy is coming continuously. So that means in this logic, if you take hydrogen, and when the electron wants to go from one to second orbit, same story. And if light was a wave, the energy is coming continuously. So this electron, right, will slowly start going out. And then it reaches n is equal to 2. But that doesn't happen, right? The electron, if you imagine, if you give electron 0.1, 0.1, 0.1, will it even take in the first place? It doesn't work that way. So you cannot explain this with a wave theory. But if you treat the photon as a particle, now it feels like, it's like a collision, like an oblique collision or a head-on collision. The electron will just simply bounce off. Think about it. Collision, there's another definition. A collision is a process in which energy and momentum are transferred in a very short amount of time. Isn't it? You're giving a huge amount of energy in one go. So this is where people realize, boss, light cannot be a wave, because you cannot explain whatever is happening. So this is what you would have noticed. If light was a wave, you would have seen a high intensity light, means a very bright light, should have emitted electrons faster. So electrons should have come out of the metal much faster. then low intensity light independent of frequency. It doesn't matter what is the frequency. Means it doesn't matter what is the energy of the photons. Second thing, there should be a time lag. So no matter how bright the light is, it will take some time, for the energy to accumulate. It's like, what? Let's say you want to buy a cycle. Cycle ka cost is 10,000 rupees. Monthly, you're getting a pocket money of, let's say, 500 rupees. So you're saving money every month, 500, 500, 500, and then you go and buy the cycle. Second case, you have a credit card. You go and just swipe the card, get the cycle. And then later on you pay the money. You see, in the credit card thing, you get the cycle in one go. You spent all the money in one go. Kind of like that. So this is what you should have seen if it was a wave, but we don't observe this. Since we don't observe this, this is how you do experiments basically. You start with thinking it is a wave and you'll expect this is what will happen, and then you see what is happening. It doesn't work, then it is not right. So photoelectric effect cannot be explained by wave nature. And this is where the people started getting confused. YDSC says it is a wave, of photoelectric effect says it is a particle. People were clueless what is happening, and they finally came up and said, okay, boss, it's called something dual nature. Let's accept that, and just people kept quiet. But can be explained by particle nature. So all these things that are happening can be explained, if you're getting a large amount of energy in a short time, like a kind of a collision. And collisions is the nature of particles. Do you guys remember if I send two waves in the opposite direction, what will happen? Can waves collide? They just pass through each other. Do you remember? If you send two waves through each other, they just pass through each other. They don't interfere. Explained by particle nature. Clear with us. So that's a bit about it. Now let's see what is the experiment and how it works out. Take a break, come back with 7, 8. We'll continue from here. Any doubt so far? We have a bit of a theory. The whole chapter is something of this sort only. We have a bit of a theory. Chalo, come back in 10 minutes. Go on. Comes on, everyone. Next thing. Now, if you look at the experiment, there, this is the setup. So here, this is a variable voltage source, meaning you can change your voltage. This thing, right? You can see here clearly, if I connect this terminal and this terminal, or if I connect this terminal and this terminal, you can change the battery cut terminals, positive, negative. So instead of every time trying to change the battery, you can actually just use the terminal. So this is useful to change the polarity of the battery. So for a simpler understanding, let me draw this. So we have a battery of voltage V. This is plus, minus. This is your emitter plate. This is your collector plate. So when light is incident on this is your incident radiation. Same picture, I'm just keeping it simple without all that ammeter and everything. You can actually draw an ammeter also, which will measure the current. So let I be the intensity. So this light which you are shining, I is the intensity and F is the frequency. So when the light falls on this surface, electrons are emitted from here. Now these electrons, right, as they're going, maybe due to internal collision or maybe due to the collision with the air molecules, what will happen? These electrons will get stuck. Did you ever see this thing when people are going in a queue or something? Suddenly, some people are just standing in the middle and talking. So it's like they just form a small group and talk. So we get something called an electron cloud. So you will find this whole region, stuck with electrons and all. So this is what will happen. So when light is incident on the emitter, electrons are emitted, and due to internal collisions, right? Internal collisions form an electron cloud. That is the reason generally we prefer to keep it vacuum inside, but yeah, some air will always escape. Now this electron cloud is completely negative charge. So what this will do? It will oppose the electrons which are coming. It will try to repel them back. So all the electrons won't reach the collector plate, which opposes the incoming electrons. Therefore, all emitted electrons do not reach the collector. So what we do here, we keep the battery here. You can clearly see this is the positive terminal, this is the negative terminal. So the collector becomes positive. So what will happen? The collector will start attracting this electron cloud. So by putting a battery, you can actually increase this current flow. This battery generates a field which will pull the electron cloud. Right? So let's see how that looks. So if you try to plot a graph here, so this is one of the graphs. So in photoelectric effect, we have two graphs and two equations. So if you try to plot a graph between the current and the voltage. So the right hand side means the collector voltage is positive. Now see, initially if your voltage is 0, you'll have some current. If you increase the voltage, the current increases. Increase the voltage, current increases, and then eventually becomes constant. We call this thing saturation current. Now, why does the current become constant? Think about it. Let's say initially 1000 electrons are emitted per second from the emitter. Because of the electron cloud, only 400 are reaching. If you pull the electron cloud, what will happen? More and more electrons will reach. So if you increase the voltage, 500 will reach. Increase the voltage, 800 will reach. Increase the voltage, 1000 will reach. If I increase the voltage, there is none, right? Everything is coming out. If I'm emitting 1000, all 1000 are reaching. Is that making sense? There are no more electrons to pull. Every electron that is emitted will come back if you apply enough voltage. That's the reason you're getting a saturation current. Be careful, this is not a resistor. Huh? V is equal to IR, voltage increases, current increases. Don't say that. There's no resistance here. So here as voltage increases, more electrons will reach the collector plate. The current will increase. And eventually, all electrons emitted reach collector and current becomes constant. This is what we call a saturation current. What happens if you reverse the battery cut terminals? Means if you make the collector plate negative, now see, if I just try to draw the picture, means you're making this plus, this minus. So this plate becomes positive and this plate becomes negative. Now the electrons which are coming out, now the force will be backward. So electrons will actually slow down. That means if you put the voltage in the reverse direction, negative voltage, the electrons will actually slow down. And if you apply enough voltage, the current becomes zero. This voltage is called V stopping potential. So if you reverse the terminals, the emitter electrons attracts the electrons and current decreases. So here we define something called V stopping potential. What is V stopping potential? This is your the potential at which the fastest moving electron does not reach the collector. If your fastest electron does not reach the collector, that means no one is going to reach the collector. That is what we call as V stopping potential. Clear with this? I hope that story is clear. This is important. You should know exactly what is happening, how is the setup, how it is working. Because if they change something in the question, you should know where you have to go and adjust. So if they ask a question like this sort, Chalo, you're saying if you apply V stopping potential, the electrons won't reach. So if we apply 10 times the stopping potential, simply if we apply more than V stopping potential, will the photoelectric effect stop? What do you guys think will happen? This is how they'll trim a theoretical question. If we apply more than stopping potential, will the photoelectric effect stop? What do you guys think? Think, take a minute, think about it. Just give me a minute, I'll be back. So what do you guys think? Again, ask yourself exactly what is photoelectric effect? Photoelectric effect is when the light is incident on a surface, the electron comes out. But by increasing the voltage, what are you doing exactly? This is what is happening when you increase the voltage. When you increase the voltage, you are actually increasing the field between the plates, isn't it? This is plus, this is minus. So there's an electric field between the plates. If the distance between the plates is d, the electric field is given by V by d. You're getting it? So the electric field will act on the electron when it comes out of the metal plate, isn't it? Think about it. if you inside the metal plate, what is the electric field inside the metal plate? Zero. Shielding effect, do you remember? That means no matter how much you apply the voltage battery outside, the field inside the plate will not change only. So once the electron comes out of the metal plate, then it will get affected by the battery. I hope you're getting it. So what is photoelectric effect? The photoelectric effect is the emission of an electron when light is incident on it. So photoelectric effect will not stop. Then what happens exactly? What happens is, when you take your emitter plate and when you take your collector plate, and if you apply exactly 1 times the stopping potential, so it will go, electron will go, and just before touching the collector, it will make a U-turn and will come back. So electrons are coming out. They're just not reaching the stopping potential. This is 1 times the stopping potential. And let's say it has traveled distance d. If I apply 10 times the stopping potential, what will happen? Then the electric field will become 10 times. That means your deceleration is 10 times. So you will travel lesser distance. So if you apply 10 times the stopping potential, you will travel only d by 10. Are you getting this? So if you apply 100 times stopping potential, electron will still come out. It will just travel lesser distance before turning back. Look at the statement of V stopping potential. The potential at which your fastest moving electron does not reach collector. Matlab electron is already out. I hope you're clear with this. So general misconception, like, if you apply more than stopping potential, photoelectric effect will stop. No. Photoelectric effect, it feels like it stopped because current has become zero, but electrons are still coming out. So just because you can't see current doesn't mean the electrons are not coming out. So electrons will travel less distance. That is what will happen. Clear with this? So changing the battery ka voltage will not affect the photoelectric effect. What it changes is your how much will the electrons travel. Any doubts on this page? You can see there's a bit of a theory, like, you need to understand properly what is happening with each and everything. The chapter is not tough. You should know your basics, and if you have done some decent number of problems, it's a very good chapter. And the reason why this chapter is important is because, they can really make weird paragraphs and ask you questions on this. Especially advanced may, they can make some weird paragraphs. So next thing, if you try to plot a graph between your V stopping potential and frequency, again, in the experiment we observe, we get a straight line. And this frequency here is your F threshold. Basically, the threshold frequency is the minimum frequency required for the emission. Now, if you look at the formula here, simple thing, energy incident. So whatever energy you're giving will be going for work function plus Ke max. This is your work function. What is work function? The minimum energy required to remove an electron. Basically, it's your binding energy. So if you want to remove an electron from the lattice, you need at least this much. Ke max is what? This is the maximum possible kinetic energy. Understand one thing. It doesn't mean every electron will come out with this energy. Remember I told you sometimes electrons will collide inside before coming out. So electrons can have any energy from 0 to Ke max. So we get two things here. So the energy incident will be h into frequency is equal to work function plus Ke max. That is one equation. And Ke max is also equal to, again, get the definition of V stopping potential. The potential required to stop your fastest moving electron. That means charge into voltage difference will be change in kinetic energy. So electron into V stopping potential must be kinetic energy. So it just comes from your basic formula there. It will be E into V stopping potential. There. These are the two important formulas in photoelectric effect. So in photoelectric effect, the two graphs, this graph and this graph, saturation current versus voltage, V stopping versus frequency, and these two things are the important ones. So this work function can be written as h into f naught or can be written as hc by lambda naught, where this is a threshold wavelength. F naught is your threshold frequency. Now in this formula here, if you substitute things, you will realize hf is equal to work function plus EV stopping potential. If you rearrange the terms, you will notice V stopping potential is h by E f minus W by E. This looks like Y is equal to mx plus c, a straight line. And you will notice something here interestingly. If you look at the slope, which is tan theta, is h by E, independent of the metal. That means if you try to plot this graph for different metals, you will observe all have the same slope. Did you ever think about this? The Planck's constant is 10 power minus 34. How did they find such a small value? Tan theta is h by E. I know the slope, I know the electron charge, I can get h ka value. And this is how you can find the constants using different experiments. That means if you do this photoelectric effect for different, elements, you'll observe it doesn't matter which element it is, all the lines will be parallel. Now, tell me one thing. Let's say if I'm using cesium, potassium, and sodium, three elements, photoelectric effect. Can you tell me which color is cesium, which color is sodium and potassium? So they'll give a question like this in mains. The graphs, V stopping versus frequency of three elements is given. One is sodium, potassium, and cesium. Which color is what? Tell me one thing. In which one is the, it is easiest to remove the electrons? Cesium? So cesium must have the least threshold frequency, isn't it? So the black one will be the cesium, and sodium is the most difficult. So green is the sodium, then comes potassium, and then comes cesium. Is that making sense? If it is more difficult to remove the electrons, that means you'll have more threshold frequency. You need to give more energy to remove the electrons. Clear with the stuff. Clear? That is the whole theory of photoelectric effect. You can see how much is there. Let's see a few questions now. Like I said, the main thing you need to remember these two, the two graphs, and have a rough understanding of how the experiment works. Let's get this. Hey, Keshav. This is a very good question, a proper mains level question. See, what is the formula? Energy incident is work function plus Ke max. So you are giving Hc by lambda. Work function, I don't know. Fastest electron means half mv square. This is equation 1. Now you made the wavelength Hc by 3 lambda by 4. The work function will not change. This will be half mv dash square. This is equation 2. Take this from here and substitute here. You end up with 4 by 3 work function plus half mv square is equal to w plus half mv dash square. So you can clearly see here half mv dash square will be half m. Send that 4 by 3 inside. You get root 4 by 3 v whole square plus w by 3. So you can clearly see v dash is greater than root over 4 by 3 v. Be careful. If you double the energy, you won't get double. That is a misconcept there. Meaning, simple numbers I'll give you, Socho. Let's say you're giving energy 100. Work function is 50. What is Ke max? 50. If I double the energy, 200, will the work function change? Nay. So what is the energy? 150. Can you see it became 3 times? The reason it doesn't work is because the equation is in the form of y is equal to mx plus c. If you double x, y won't double. This is not a proportionality. Y is not proportional to x. There's a constant sitting beside. Are you getting this? So be careful. Huh? These are one really good questions at a mains and bits level. If you double the energy, you won't get double and all. You'll get greater than or less than types answers. All clear with this? The next one. The next one is an important one. So let's say I'm drawing a graph between the current and the voltage. Let's say this is the graph for intensity I and frequency f. So when you do the experiment for a light of intensity and frequency f, this is the graph. Vf is your stopping potential. So using this graph as a reference, can you draw the graph if you double the intensity and double the frequency? How will the graph look? Double the intensity, keep the frequency same. Keep the intensity same, double the frequency. Can you draw the graph for these three? This is a pretty good one. And if you look at NCIT, right, smartly they did something. I'll tell you what it is. And because of that, people start thinking, we get a wrong concept. Try. Take 2-3 minutes. Think about this. It's a worthy question. Let's see. Now, listen what is happening here. Few things. If you increase the frequency, if F increases, the kinetic energy maximum increases. I won't say exactly double or something. Ke max increases. The electrons will come out faster. Because the electrons are coming out faster, I need to increase my stopping potential to stop them. So this much is clear. If you increase the frequency, stopping potential increases independent of intensity. This does not depend on your intensity. Second thing, when you say intensity, this is the important one, everyone. Intensity is power by area. What is power? Energy per second. What is energy per second? This is number of photons per second into energy of the photon, which is h into f by area. That means if you look at here, intensity I is proportional to n into f. N is the number of photons per second. And how many electrons you emit will depend on, so the current is proportional to number of electrons per second. Number of electrons per second into charge will give you current. And number of electrons per second is proportional to number of photons. If you have more photons per second, you get more electrons, therefore you get more current. Now the mistake here people do is they think if intensity increases, current increases. So let me give you a rough analogy, a weird one. Listen to this thing. Let's say I am running a shop, right? And I have a weird policy in the shop. So I'm selling toys. The cost of one toy is 100 rupees. So in my shop now, this is the policy. You give anything less than 100, you won't get a toy, obviously. But if you give me anything more than 100 rupees, you will get a toy, but you won't get the change back. Meaning, if you give me 100 rupees, I'll give you a toy, done. If you give me 200 rupees, I'll give you a toy, I won't give the change back. If you give me 500 rupees, I'll give you a toy, I won't give the change back. If you give me 2000 rupees note, I'll give you one toy, I won't give the change back. Do you get in the policy of my shop? So for one note, you get only one toy and you won't get any change in return. Now let's say you and I both are carrying 1000 rupees, but I have all 1000 rupees in 100 rupee notes. You also have 1000 rupees, but you have all 500 rupee notes. So simple question, do you and I, don't we both have same amount of money? We have same amount of money, that's your intensity. But do we get same number of toys? You're getting the problem there. So here, toys are the electrons. The number of nodes are the photons. The value denomination is your frequency. If you give a high frequency note or a high denomination note, right, the excess energy becomes kinetic energy. That is lost. You cannot share that between different electrons. Are you getting what is happening? Even though for namesake we have same money, we can't buy the same number of toys. Are you getting the catch? For example, let's say I have 1000 rupees. So 1000 rupees is 10 notes into 100 rupees. Now what I did, I made the money double. But how did I double the money? I made the denomination 200 rupees. Will I get more toys just because I have more money? Are you getting the problem? My money increased, denomination increased, the number of notes didn't change. So this was the mistake, that happens if intensity increases, current increases. Not true. So let's see how to use this thing then. So if you go to the graph, so current does not depend on your intensity. So this is for I and F. And we saw I is proportional to N and F. If you double I and F, if you double both of them, N does not change. Therefore, current remains same. And this is a mistake. So in NCERT, what they did, smartly, they gave a case for I and F, they gave a case for 2I and F. So they made sure to keep F same. This gave an illusion, if you increase intensity, current बढ़ जाएगा. I hope you're getting it. Because if F is same, then I is proportional to N, right? But what if you start messing up with the frequency? Current remains same. So this is how the graph will look. This is your stopping potential for VF. So the graph will start from here, V2F, because if you increase the frequency, stopping potential will increase, but the saturation current will remain same here. This is for 2I and 2F. Make sense? Even though intensity increase, the current remains same. This will be the graph for I and 2F. Yeah, this is a graph for I and 2F. If you keep the intensity same and increase the frequency, number of photons will decrease, so current will decrease. And the stopping potential will be same as 2F. This will be graph for 2I and F. If you keep the frequency same and increase the intensity, you get more photons, so you get more current. Please check the graphs. All clear with this? This is an important thing. Current depends on number of photons per second, not on intensity. Any doubts on this? So let me show you how they'll frame this as a statement question. So graphs is good one. They never asked anything like this. But if you try to put this as a statement question, it would be of this sort. Let's get this. Right then. Yeah. See. So just now we saw. So I is proportional to NF if you double both of them and remain same. Therefore, current is same. Now, people who remember that, increase I, current increases, they will goof up and come. And same thing here. If you look at that, you're increasing the frequency also. So HF is equal to work function plus kinetic energy K1. Then if you double the frequency, this will be H into 2F is equal to work function plus K2. If you substitute here, this will be 2 times W plus K1 is equal to W plus K2. We get K2 will be 2K1 plus W. This is what I was saying. You'll always get more than double here. It's a pretty good one. You combine the previous two questions into one. So current remains same, and whereas the kinetic energy will be greater than 2. Clear with this? The one thing you'll notice in this chapter, questions will be different, but once you get a hang of it, they're actually pretty easy to solve. That is the reason you need to do around like some 70, 80 questions and it will be done. I'll send you a small sheet also on this today. You can try that, maybe some 15, 20 questions. Let's see one more. Now look at this setup here. This is where I'm saying if you actually know how the setup works and if you can draw a picture every time and visualize, you will get that understanding. So if you look at this picture here, the collector voltage is at 2 volts. So this is plus, this is minus, this is 2 volt. So this is 2 volts and this is at 0 volt. So here the energy of the photon, let's see, this is 12400 by 2000 angstroms. That will be 6.2 eV. Work function is 4.5 eV. Therefore, Ke max will be 1.7 eV. Now remember, this is the maximum kinetic energy of the electrons. That means electrons at the emitter can have energy from 0 to 1.7. Everyone won't come out with 1.7. And what is this battery doing here? Since you're giving 2 volts, think about it. The energy gained will be charged into potential difference. So this collector voltage is giving you additional 2 eV. So here, this battery, so whatever electrons are coming out, doesn't matter which electron it is, it gives everyone 2 eV extra. Battery gives additional 2 eV to the electrons. That means the electrons which came out here, they will have energy from 0 to 1.7 eV. By the time they reach the collector, so when electrons reach the collector, all of them have gained 2 eV. When electrons reach collector, they have energy ranging from 2 eV to 3.7 eV. Are you getting it? Everyone doesn't have 3.7. Now let's look at the option. The minimum kinetic energy of the photoelectrons on the collector is 0. Collector is saying, not emitter. Minimum energy is 2.2 eV. This is wrong. Maximum kinetic energy 3.7. This is right. If the polarity of the battery is reversed, now understand one thing here. Here, what is V stopping potential? Here, V stopping potential is 1.7 volts. So here, the V stopping potential for the question is 1.7 volts. And if you reverse the battery, you're applying 2 volts. 2 volts is greater than V stopping potential. Therefore, electrons won't even reach the collector. If electrons are not reaching the collector, what are you talking about? Minimum kinetic energy. If the electrons reach the collector, you can talk about minimum energy, isn't it? So none of the electrons will reach the collector. They will turn back even before reaching. That's why when you reverse the polarity, the minimum kinetic energy is not defined only. Obviously, the fourth is also wrong. Only B is the answer. Check. Are you getting why C doesn't work? Since you're applying more than stopping potential, electrons won't even reach the collector. So there are no electrons at the collector. So there is no meaning of saying the minimum energy is 0. All clear with this? Clear? Any doubts on this? That is your main theory there. So next class, when you catch up on Thursday, we'll continue from here. We will see few more good models on this. There are another 3-4 models on this. And then we will go ahead with the next part, Bohr's theory. Like I said, that is another important thing. So okay, with that, we'll wrap up for the day. I'll also send you a small sheet today. You can give it a try. So we'll catch up again on Thursday, same time. So any doubts, anything else, please stay back and ask, or else you're free to leave. I'll see you guys on Thursday. So take care, stay safe.